Hello. So we are going to study chapter 3.3.3, 3.3.2, excuse me, which is on page 80 in the textbook. So it's continued from the Thursday lecture on March 2nd. Okay, let me start. So in the last class, we studied the matching estimator. Um, so the matching estimator is defined this way. The idea is just to match the characteristics x, the control variables, across the treated group and the control group, and compare their average outcomes, right? Given the same characteristics. So you compare the people, those who have the same characteristics across control and treatment groups. And to interpret this difference as a causal effect, we need the conditional independence assumption, which means the potential outcomes are independent of the treatment decision conditional on X. We have studied this assumption several times, and this assumption is to remove the selection bias. If this assumption fails, then that implies this estimator has a selection bias. So that was the main topic in the earlier part of this course. So now we are going to assume that this assumption is true. If this assumption holds, then we learned this estimator, matching estimator, equals the average treatment effect conditional on the characteristics. So because we restrict the characteristics to be lowercase x, so what we get is the treatment effect, average treatment effect for those guys. Okay, so this is a brief review of what we have done earlier in this course. And so it is nice because we wanted to know this. This is what we want. The average treatment effect is what we want in the end, in many cases. But as I said, it is unknown. The potential outcomes y1, y0 are potential. They are latent. They are not directly observable. But like under this assumption, we can express these potential outcomes only using observed variables, observed outcome, treatment decision, and observed characteristics. So that's the reason why we make this assumption and this estimator. But I have mentioned this problem many times. It's nice. So technically, the matching estimator is nice, but the problem is when there are many variables in X, then computation is a problem. Like here, I explained it this way. So if the control variable X has k number of variables, like say 10 variables, which is not a lot in practice. So in many analysis, you use maybe more than like 10 or 20 variables as control. So then, and if each of them is binary, then already there are 2 to the exponent of k number of different characteristic groups. So it's increasing exponentially as k increases. So easily it will go up easily to a large number. So that will cause a problem. If k equals to 10, then 2 to 10 equals like 1,000, more than 1,000. So you have to divide the data into 1,000 subgroups, and you have to calculate the averages for each of the groups. So it is a problem in practice, and your estimator will be inaccurate because your effective sample size is smaller for each subgroup. And this problem is referred to as the curse of dimensionality. So as the dimension increases, the problem increases exponentially, not proportionally, but exponentially. So it's easily out of our control, and we cannot handle this problem. And of course, we know the answer. We know the remedy. We need to reduce the dimension. It's a simple but clear solution to this problem. So the goal of this section is the main ultimate goal of this section is to find a way to reduce the dimension without losing any information. That's what we want. Okay. So this idea already exists in statistics. In the statistics literature, it's called sufficient statistic. So what we want is, instead of matching all the each variable in the control, we would like to summarize the information in all the characteristics into one variable. That's what we want. That's the dimension reduction, right? So for example, we hope to transform x. X is a multiple variable actually. X is a vector. It contains multiple variables, but by taking some function, transform the variables into only one variable, which we define as p. So if you can define something like this, and we hope this variable to satisfy this formula. Exactly, this is the left hand side is the matching estimator based on the new variable, and the right hand side is the average treatment effect based on the new variable. So as you can see, if you compare this statement to this one, the new variable p replaces x, the role of x. The p is playing the same role as x in our original matching estimator. So this is exactly what we want. If you can find this kind of variable, then you don't need x itself, but p is good enough for our purpose. We just wanted to express the potential outcomes using observed variables. That's our main reason using this equality, and p can do that, right? That's what we want to do. And also in this case, because p is one dimension, so there is no curse of dimensionality, right? So it's just one dimension. There is no dimension more than one. So it's nice, and your estimator will be more accurate statistically. Will be statistically more significant. So that's what we want and what we are going to do, and it's called sufficient statistics in statistics. In statistics, and in here there is no s. This is correct. This is wrong. And then to think about such a variable, what is a sufficient information in our analysis? Then we will go back to the decision-making process. We will revisit the treatment decision-making process, because this is where we choose the control variables x. Earlier, I told you that the control variables x must be the variables that affect the treatment decision, not affected by the treatment decision, but x affects your, for example, college decision. Okay, so d x affects d, so we can write this as a kind of function, right? The decision is made. Your decision is a function of control variables x and something else, ui. U is just a collection of unobserved components. So U is an unobserved component that is independent of the potential outcomes. So this does not cause any problem because it's independent of the potential outcomes. So this part is well behaved, and in this case we call this selection on observables. So selection, the choice, is made based on observables and independent unobservable. That's the definition of selection on observables. Like earlier, I used this example. College attendance decision. Think about, we would like to estimate the effect of college degree or college attendance. And then, to think about the control variables we need in our analysis, we have to think about the determinants of your college attendance. For example, your high school GPA, or financial aid availability, or your family income, or distance to college, and job market for high school graduates, like unemployment rate for high school graduates, right? Things like that. You may include more variables if possible, like parents' education level, or region, age, like year, or like a lot of variables. A lot of observed variables can be included in X as long as it affects your college attendance decision. And still there are remainders. Remainders are just collected, observed into U, and let me just call this the log. Still, there is a randomness in the admission process, admission decision. So, some good students are rejected, but worse students are accepted sometimes. So that happens, but that's purely kind of luck, pure randomness. So, if you think about this, then now this helps you understand the role of X. The reason why we are matching those characteristics is because if X is the same, then basically the decision will be random. Because U is, when X does not change, then the decision is based only on the unobserved U, which is random, independent. Okay? So that's what we want. Then, extending that idea, then we can find that what actually matters in our analysis is not X itself. We don't need the detailed information of X, but we want to think about the effect of X on your decision. That's more important than your family income, or your parents' education. They affect the decision. The way how they affect your college decision is the key part in our analysis. So let me give you this example. Think about two students, high school students, who think about their college attendance. Student A, the first student, is from an affluent family, but academically, this student is not that good. But there is another student, say B. Student B is not from an affluent family, but this student is academically better. So, and I assume that, so the student A has good and bad, and bad and good. Student B has bad and good in terms of attending college, and assume that these two students have the same probability of attending college. Then, in our analysis, in our inference, we don't need to distinguish these two students. Their family income and test scores are different, but in the end, their probabilities are the same. Their probabilities of attending college are the same, so theoretically, they are identical in our analysis, right? Do you get the idea? So again, I said what we are interested in is not, we are not interested in their family income, but we are interested in their probability of treatment decision, right? So then you can balance out across X, right? You don't need to have identical variables in X, but overall, if the probabilities are the same, theoretically, they play the same role. They are the same counterpart. They are counterparts to each other in our analysis. So this is a summary of some casual way to explain the mathematical derivations in the textbook. Okay, I tried to avoid any mathematical expressions, but intuitively it makes sense, I believe. Okay, then we call this the propensity score. Propensity score variable is defined this way. This is the PI is probability of choosing the treatment conditional on the characteristics. So your family income, your high school scores, and distance to college, and all the factors you observed, and then you can calculate the actual probability of that student coming to college. That is the sufficient statistic. That's sufficient. This is what we want actually. This information is sufficient. And then, as I said, if two observations have the same propensity score, then we can match them. That's the desired result we wanted. Okay. Okay. Let me stop here. I'm going to continue from here about how to utilize the propensity score and some useful results based on the propensity score, and then more actual data analysis. Okay, see you in the next video.